In this chapter, we'll start looking at detectors and overall design of spectrophotometers for UV with radiation. We'll never touch it. So most spectroscopic instruments, as you already seen, requires source, monochromator, sample. That's what we already look at. And then we need detector and data processing unit. So I will start with looking at detector in today's design and then look at overall design, how all these things can be assembled together. Phototube, the simplest and oldest, very robust and inexpensive detector. Response phototube or very similar photomultiplier results from photoelectric effect. Phototube consists of cylindrical photocathode and a wire anode sealed inside transparent glass or, for UV light, quartz envelope. Concave surface of cathode supports layer of photoemissive material. That's usually alkaline metal or other metal oxide that emits electron when radiated with light. When voltage is applied across electrodes, 90 volts here, emitted photoelectrons attracted by anode. These electrons produce a current which can be amplified and measured. Number of photoelectrons ejected from photocathode per unit of time is directly proportional to power of beam striking the surface. These are examples of sensitive materials. It's gallium arsenide for area from UV to near infrared, silver cesium oxide for visible area only, or very sensitive potassium cesium antimony alloy. There are plenty of others. So let's look what happens. Photon is coming, striking, and the electron is coming to a node. Photomultiplier has exactly the same electrode here, but after that it has very sophisticated multiplying design. So first photon is striking here, next electrons are flying to the next electrode. We name them dinode. So D1, it has positive voltage over photoemissive cathode. Now, when it's striking, it emits more than one electron that in turn strikes D2, resulting in even more electron going to D3, and so on 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 until it reaches the wire anode. So instead of one, we had series of electrodes, so total voltage will be around 10 times larger. We are talking about not about 90 volts, about thousands of volts. The whole tube will look like this. Let's look at scheme. So photon will strike 2, plenty, even more, and so on, so on. More recently, different designs of solid-state detectors appeared. They are smaller, more robust, and less expensive. First is photodiode. What is that? Diode is a device that conducts current only in one direction. In this case, it's achieved by having silica semiconductor doped with different elements. N-type, negative type, has extra electron because it's arsenic with 5 electrons. P-type is doped with gallium that has 1 electron less. Now, in depletion region between two of them, there is a possibility to increase the current through the system if photons are striking. So if photon strikes this depletion layer, current through the system increases, and this current will be proportional to number of photons, proportional to power of light. Silicon diode detector is more sensitive than usual phototube. You can arrange these small detectors, size around 0.02 millimeters, in a chip or array. So you have diode array detector containing usually 2 power 10 2024 or 2 power 9 512 or 2048 2 power 11 elements. That still makes it reasonably small, couple of inches. If one or two such detectors are placed in monochromator, all wavelengths can be monitored simultaneously, making possible high-speed measurement of the whole spectrum. Again, for current in each element is directly proportional to incident radiant power, so you can measure thousands of wavelengths simultaneously and very high speed. CCD and CMOS detectors, similar to those you have in your photo or video camera or say in smartphone, are also very useful detectors for spectrophotometry. They are less expensive than diode arrays and sometimes more efficient. Let's just compare how many photons you can detect with different devices. For 1 second, a phototube requires several thousands photons. Photomultiplier requires almost 100 times less, same as charge-coupled device. When exposure time increases, you have better readings for phototube, but much better for photomultiplier tube. You can see it's in vicinity of 1 photon per second. And charge-coupled device is simply proportional with time, so beyond 100 seconds you need less than 1 photon per second to see this signal. The same sensitivity is for visible light as for UV light. Now coming to overall design system. A single beam spectrometer, most common and relatively inexpensive, has source. Radiation is coming into filter or monochromator. Then you have shutter. Shutter is very convenient tool because you do not want to switch your lamp on and off. It can damage the lamp, so you simply cut off beam with shutter. Then beam is coming to the cell compartment. You can put reference cell, or you can put the sample cell exactly in the same position. Then beam is coming to photodetector, so you have two readings, one from reference, one from sample, and absorbance can be calculated. Double beam system has several designs. One of them is such. Lamp is giving photons coming through monochromator. Then you are coming to beam splitter. You have V-shape mirror, and the beam is coming here and there with exactly the same intensity. You always have shutter before that for the same reason. Now, two beams are coming through two cells exactly simultaneously. So whatever changes happens here are the same in a reference and in the sample cell. And then the resulting light is detected by two different photodetectors. The difference is amplified, recalculated, and you have absorbance. Most popular beam splitter is beam in time. How does it work? Two beams are separated by rotating mirror here. So at one moment beam is going directly. When the beam splitter is appearing in view, a light is reflected toward this mirror and going through reference cell. Back force changes happen 1,000 times in second if necessary. So essentially you have continuous beam of exactly the same intensity at both positions. One mirror collects two of them at the same point, and then the intensity are compared. There is optical wedge here or electronic wedge that makes these two beams exactly identical, which is much easier to detect. Double beam in time approach generally preferred because you have one detector only, so quality of your readings are much better. You are not making mistakes because of mismatching of two detectors. Let's look at how this design can be realized. So here we have diode array instrument with single beam design and 1024 diode array, which covers 190 nanometer to 950 nanometer. With multi-channel system, dispersive system is grating placed after sample reference cell. Photodiode array, or it can be CCD array placed in focal plane. You can measure the whole spectrum in less than 1 second. Of course, to process data with 1000 elements, you need a computer. Array dark current is acquired and stored in memory. Then you run the spectrum of this source with no compounding your cell. So you have your blank, and then you run your sample. All these numbers can be quickly calculated by computer, giving you absorbances. In this particular, there is holmium oxide filter that allows to automatically check the wavelength calibration. There is tungsten lamp and deuterium lamp running simultaneously for the same system. Here is research level double beam spectrophotometer running for very wide range from 175 to 1800 nanometers. Double beam instruments offer advantage that they can compensate for all fluctuations in output of source. They can compensate for wide variation of certain intensity with wavelengths. So if you want to record high quality absorption spectra, this is your choice. Now, this particular instrument has so good detector and so little stray light, you can measure absorbances up to 8 absorbance units. Remember, we do not want usually to go above 2, but here you can do. So how does it work? The beam is coming from the lamp right here. One lamp is tungsten, another is deuterium. One of them coming to this mirror, one more mirror, one more mirror. From this mirror, it strikes this very mirror, from where it goes to grating. From grating, you have wavelength separation. Again, by mirror, it's directed towards another grating. And here we have one more bounce, then again to the same grating, so even better separation of the beam, after which it goes to the same mirror and escapes through the slit. So essentially you have 3-time separation of close located lambdas. As a result, you may have very high resolution. So the resulting beam is coming to rotating chopper here, which sends one half to this mirror and one half to this mirror. You have 2 cuvette positions and very voluminous large cuvette compartment. You can put lots of good tools for your cuvettes here. So then light is coming to this mirror and approaches the detector. So again, system that works for detector. Then you have embedded computer in the same instrument. Very sophisticated, very nice tool. Now both designs are shown in 2 videos that you can find in your Blackboard